Welcome to the screencast of constant and changing motion problems. At this point in the year, you've spent a fair amount of time looking at position and velocity time graphs as a way of explaining what's going on in constant motion situations. And this was one example that we did where we had an airplane that travels at a fast but a steady speed. The thing that makes these problems really easy is that because the speed's not changing, they're picking off a steady number of meters every second, and you can understand them by just using one formula. What we're going to do as we go forward is use velocity time graphs, especially as a tool for understanding complicated situations, because there's a lot more that's going on in the real world than just steady speed. And this turns out to be the most important skill you can have in understanding the motion of objects, how to use velocity time graphs to explain what's going on with them. So a situation where that would occur would be one like this, where we have a speeder who zips by a police radar trap at some speed right there. And they don't ever tell us that the speeder speeds up, so we're going to assume that that means that's a steady speed. But we also notice that the police car can accelerate, and they give us this term right here. So one of the things that you want to make sure you get coming out of this screencast is a real comfort level with what that unit is, meters per second per second. And what we're going to do is we're going to use a velocity time graph to start to get that comfort level. So away we go. So as you can see right here, what I've done is I've created a little velocity time graph. Now I did one thing right away that you might not have been able to do. I've done this problem before, so I knew that this speed right here was going to be handy to have. But what we're going to get in the habit of doing is drawing a velocity time graph and feel comfortable not knowing what the speeds are. Just based on this problem here, if I drew a velocity time graph, I knew that the velocity of the speeder was going to clock in at 30 meters per second. And it's pretty easy to draw that line. It's just a nice steady velocity, so it looks like a horizontal line on my velocity time graph. This unit right here we want to stop and look at for a minute. It has a couple of units in it, and it's super important that you understand what this is. An acceleration has seconds down here and meters per second up here. And when you look at it that way, what it's trying to tell you is that for every second that goes by, this police car can speed up by 5 meters per second. So when we look at a velocity time graph, that's pretty easy to understand. So what I'm going to do is I'm going to say that if the policeman starts at 0 speed, 5 meters per second means that every second that goes by, he's going to increase by 5 meters per second. And you can think of it just as counting on your fingers almost, where I'm going to watch his velocity go from 0 meters per second to 5 meters per second to 10 meters per second to 15 meters per second to 20 meters per second, so that it's actually not hard for me to find out that by the time 6 seconds rolls around, he's traveling at a speed of 30 meters per second. So that's the essential thing that you want to get as you look at velocity time graphs. They let you cover all sorts of situations, ones where you travel a steady speed, and ones where you're speeding up, and also ones where you're slowing down. And also, you see how we can handle the idea of acceleration on those graphs. So we're just going to turn our attention now to a situation where we're going to look at a couple graphing techniques that you can use on velocity time graphs. In this slide, what we're going to look at is two techniques that you can use to understand motion when you have a velocity time graph. So in this story, we've got the grudge match between rabbit and turtle, and what this graph is telling us is that both animals start with 0 velocity, both animals speed up somehow, and then they both do different motions. So the story for the turtle is that he travels, or speeds up rather, from 0 to 2 meters per second, and then he cruises along at a steady speed until the race is over down here. The rabbit story is a little bit different. What he does is he speeds up, travels a steady speed, and then slows down again. So we definitely don't have a constant speed, although there is some constant speed in this problem. And what we're going to do is use those two graphing techniques we talked about. The first one of those is the idea of slope. So on a velocity time graph, slope is equal to acceleration. So if we wanted to know the acceleration of the turtle, right down here, that's an area right there where he does have an acceleration. And the way I use it is the same as I always use slope. Slope's rise over run, or it's change in y over change in x. But I'm going to adapt those labels just a little bit and say acceleration equals rise. So rise, this time, is change in velocity, over run, which is change in time. And if you see, I just invented a new formula, and we're going to see that formula a lot. So for the for the turtle, it looks like he gained 2 meters per second over that first chunk of time that was 60 seconds. And what you see is that unit that we just talked about a minute ago. You see 2 meters per second over 60 seconds. It's a little number. I'm not really worried about it right now, but I have meters per second over seconds, and I just want you to notice that. So first thing you want to know on a velocity time graph is that slope is acceleration. Now the second thing that we can get from velocity time graphs is how far we've gone. So it's not as simple as distance equals velocity times time, but it's not really too tricky either. The idea is that the area under a velocity time graph is equal to the displacement that you underwent during that time. So just to pick a section, what we're going to do is look at this section out here where it looks like the rabbit sped up, traveled a steady speed, and then slowed down again. So the way you handle area would be like the way you'd handle area in geometry class. This looks like a triangle, this looks like a rectangle, and this looks like a triangle. It's the same as the first triangle. And all you need to do is just watch how the labels work as I do area. So the first thing we're going to try is area of the box equals 1/2. Let's get rid of that layer right there. The area of the box right here is going to be base times height. And so base times height looks like a base of 60 seconds times a height of 4 meters per second. And there you have it. So during that time right there, the rabbit traveled 240 meters. You're going to be able to do the same exact thing with the area of the triangle, except you just have to remember what formula you're going to use for the area of the triangle. That's a little bit different. Area of the triangle is going to be 1/2 base times height. And we're going to use the same trick. It's going to be 1/2 of the base of 60 seconds times the height of 4 meters per second. And we get that the rabbit went 120 meters during that time. And using that technique of getting the area of the shapes, you'll be able to add them together and figure out how far people went as they do complicated motions. So in the next slide, what we're going to look at is how these play into formulas and how we can link these two ideas together to solve practically anything. So here we go.